area of the solid state sciences as a diploma and PhD students, there was a certain imagination and certain theories were moving around, and the community of solid state chemistry was divided into two camps. In one camp, people were sitting, making structures and believing in structures and trying to learn from these structures systematics and understand solid state chemistry and try to predict some things from these ideas. And for me, even as a student, I felt very uncomfortable with this approach. Of course, we have to know the structures, but these are just descriptive issues, and they do not allow predictions. In particular, geometry is the result of something, and it's not the cause of something. So the cause is always, you have to look for it in the scheme of energetics and of entropy and entropy. So this is, I was not happy with this one. And in the opposite camp, people were sitting who were believing in thermodynamics, to be precise, in equilibrium thermodynamics. And so the idea behind synthesis planning of these guys was to estimate the thermodynamic stability of a potential compound with respect to the elements. And even my professors draw this cartoon at the blackboard, just a lake, or they called it the mud of thermodynamics, and the surface of water they associate to delta G equals 0, and below the surface, delta G of formation is positive, above negative. And then they are telling, well, any plant which is below this surface will never exist. Only those who look through the surface, only with the tip, will be able to exist. And this is one of the worst misconceptions we ever had in solid state chemistry, because thermodynamic stability is not a sufficient precondition for seeing all compounds that can be made. And it's very easily explained. Most of the material around us and most of the compounds we synthesize in the lab are in a metastable state. So this is really a bad thing, and the literature was full of such predictions, and they really discouraged to try certain synthesis because they said, well, this will not be thermodynamically stable. This field of equilibrium thermodynamics, this field of exploring phase diagrams and documenting equilibrium states of matter in phase diagram belongs. This, on the other hand, is of course a very relevant approach, because these phase diagrams are really encoding the thermodynamic stable materials, and it's of particularly useful in the field of intermetallics and in high temperature ceramics and materials. Well, but all these approaches are descriptive. So from such a phase diagram, predictions are not possible, although there exists a program system called CALFAT that allows to extrapolate into unknown parts and region of the phase diagram and to optimize the phase diagram. But it's not predictive. It's not predictive at all, this phase diagram. But now, anyway, very helpful. Well, now this equilibrium thermodynamics, this building of theory is, I think it's really elegant, and I like it because it is controlled by stringent laws. You can handle everything in a mathematical sense. And so the fundamental statement is that for any given material system, you select some number of elements, put them into the closed system, and equilibrate them. Then what will be present in the system at phases and even the components' activities will be unambiguously determined by the variables of state. So this is a very fundamental thing. And this is why these phase diagrams are so important. So these are really, for me, the keystone or a kind of foundation in solid state chemistry. And it's the first one. In a minute, I will present the next one. So this is unchangeable and fully fixed and determined by natural laws. Well, now let me come to my thinking considerations about synthesis planning. So the former approaches, I was not happy with them, and they were not really successful. And I started my thinking with in a very rigorous way. So I started with considering the whole body of arrangement of atoms that are possible. And all these configurations or all these structures, really any arrangement possible is considered, even those who are physically or chemically not meaningful. This is, of course, a huge space, well determined, and the number of configurations will be infinite, definitely. But to each of these configurations, each of these arrangements, there exists this associated amount of potential energy. And that means we have these two spaces, the configuration space and the hypersurface of potential energy. And there's a one-to-one relationship between these two spaces. And in order to help a little bit your imagination, I just show here a three-dimensional section of this space. And this is this landscape of potential energy. And to any dot on this space belongs a configuration, a structure. For chemistry, however, only those structures are relevant that correspond to a local minimum on this surface. And still, the number of these local minima will be infinite, innumerably infinite. And this view of projecting the chemical world onto this energy landscape is very beneficial, because it first it gives you the feeling and the knowledge that any compound, any configuration that can exist, any material that can ever be made is already present on this energy landscape. And another issue is very nice and important. So from this section, only the deepest lying minimum corresponds to the equilibrium phase. All others are metastable. And so this creates a correct relationship between metastable matter and thermodynamically stable matter, the ground states of matter. Well, now, and you see these arrows are just indicating how pathways in chemistry might work. This is just a cartoon, but I hope it really helps supporting your imagination. And so this landscape of chemical configurations of potential energy, it is a landscape that is calculated for 0 Kelvin. And this landscape, again, is unchangeably determined by laws of nature. And this is the second keystone in solid state chemistry. So now we have two of these anchor plates. First, the ground states of matter, documented in phase diagrams, and if they are determined correctly, let us assume this. And then this hypothetic potential energy landscape at 0 Kelvin. And this also cannot be changed by chemists nor by anybody else. Well, and now the question comes, can we relate these two spaces, the space of ground state matter, so the thermodynamic space or the phase diagrams, and the potential hyperphase of all chemical configurations? And so this is now another representation of a phase diagram. Phase diagrams are just projections of the G functions onto the variables of state P volume T, P or volume T, and the molar fraction. And these are the curves associated of free enthalpy associated to these three phases existing in this hydrostatic system. Now, you see, this system does not have any atomic coordinates, only thermodynamic variables. So you will see immediately it is impossible to generate, starting from a compound sitting on this curve, the gamma phase, to find any other new compound. So it is not possible to try any prediction from this starting point. And this is, of course, related to the configuration plate because this compound, gamma, has a certain structure. So it is present in the configuration space and on our potential energy landscape. And now comes into play this our potential energy landscape, and to each of these phases, a local minimum belongs. And if you want to find new structures, particularly new structures, we have to transfer the known structures from this phase diagram to this configuration space and to this potential energy surface. And then we can start from such a minimum structure here and allow the random walker, the means how we explore these landscapes, the random walker, and increase the energy and allow to walk around and to drop in one of these other minima, finding new configurations. And then we can go back to this phase diagram, and at 0 Kelvin, this is a continuous landscape. At finite temperature, all these high energy regions decays, and all the configurations that are stable at this temperature, or microstates, are accumulated in these lower tips. And by thermodynamic integrating over these microstructures, micro configurations, just applying statistical thermodynamics, one can calculate the free enthalpy of these compounds as function of these variables. And now we have really created a connection between these two. Here, the phase diagrams, equilibrium states without any predictive power. Then we can move to the 0 Kelvin landscape, potential energy landscape, search for new configurations, and go back to finite temperatures. You immediately see the limitations. So the limitation of this anchor plate of equilibrium thermodynamics is that we never know if we are truly in equilibrium, in particular in solid state chemistry. It's difficult to answer. For the potential energy surface of chemical matter, the problem is that it's only valid for 0 Kelvin. And of course, we will never be able to arrive at 0 Kelvin. But anyway, we have been using this concept, and this has given me a really firm feeling, and I recommend to everybody to think in terms of these two landscapes if you think of chemistry. And so these are really true anchor plates, and between these two firm anchor plates, the shaky ground of real chemistry happens, and with all its mysteries and so on. But anyway, starting searching this landscape is revealing new compounds and new compositions, new structures, and most of them are also stable at finite temperature because the entropy you have to add is in most cases small for solid materials. I will only show you one example, just a proof of concept for our approach of doing synthesis planning by searching the potential energy landscape of chemical matter. And so it starts, well, I should mention that on this potential energy landscape, this allows to take a holistic view at chemical synthesis. Any action taken in chemical synthesis is meaning that we are moving around on this energy landscape of chemical matter. And all these methods applied in former times and up to now all take place on this landscape. And so this view is really unifying all these different approaches to solid state synthesis. And you all know the least controllable is a typical solid state method. It's the trial and error or bake and shake approach. And then one can go to analogies among the elements in the periodic table and derive ideas for synthesis, or can use the crystal chemical rules. It is just the idea of starting with the structures. And of course, Goldschmidt's approach to explain perovskites is one of the most famous ones, and so on. And our approach is here at the very end, where we use the energy as the only cost function. And we globally optimize this landscape or search this landscape for structure candidates. And the limitation of the landscape is only given by the kind of atoms and the number of atoms, into not even the numbers, but just the system, whether we give 3 different atoms elements of 4 or 2 only. And I'll show you a very illustrative example. Sumik mentioned it already in his introduction, which is absolutely convincing and shows that our approach really works. You all know probably that lithium nitride is an extremely interesting compound. So it forms just from the elements. And if you heat lithium in nitrogen, then it starts burning. It's an amazing effect. So it deliberately enters this compound. And so if you would ask Dmitry Mendeleev, do you expect sodium nitride to exist as well? Of course, he would say yes. Yeah, it will exist, absolutely sure. But generations of solid chemists had tried to synthesize this compound and they failed. All these attempts failed. And moreover, the guys from the thermodynamic equilibrium camp came along and calculated the stability, potential stability of this compound. And they said, sodium nitride will never be stable against decay into the elements. So they say it cannot exist. Do not try, do not invest any work in making it. So we asked our random walker searching the global landscape of sodium nitride, just these 2 elements, and searching what all is present on this landscape. And here we found many structure candidates, and here the lowest 6 are given, only generated by the computer, and we do not give any pre-information, nothing, only the elements, not the composition, nothing, only the elements, the 2 elements. Then we arrive at these 3 structures, 6 structures. And there are more at higher energy even. And this is really amazing. But what is true also for our candidates, all candidates we found, they should decay into sodium and nitrogen, in dinitrogen, at standard conditions. So they are metastable as was predicted by others before. But in parallel to these computations, which are a kind of computational annealing, we went back to experimental annealing, and using just a kind of MBE setup, we deposited just the starting materials in atomic dispersion on a substrate. So we did not mix them in a mortar, with pistol and mortar, as is normally done in solid chemistry, but we cracked them into atoms, and even nitrogen was cracked into atoms by a microwave plasma. And the nitrogen atoms and sodium atoms were collected on a substrate, and when warming up from liquid nitrogen temperature at very low temperature, this mixture started to react. And at room temperature, we harvested this compound having this diffractogram. And this was one of the greatest moments in my career as a researcher, to see that exactly one of these predicted candidates was synthesized in 1 step and almost in pure state. So some moisture entered the system, a little bit of sodium hydroxide had formed. And the stability of this compound ends at 80 degrees centigrade. So one understands that it was never could never have been achieved to synthesize sodium nitride along conventional routes of solid-state chemistry. So a great success, prediction and realization, but not the most stable one of the of higher energy, the anti-rhenium trioxide type. Well, interestingly, in the same institute, there were colleagues who did not believe us. And so they tried to check us, and I'm very happy that they checked us, and they really confirmed our discovery of this starting material, and they put then material into a diamond anvil cell and subjected it to pressure. And with increasing pressure, 4 of these phases, and this is very close, it's a slight distortion of the sodium nitride 4 type, was discovered. And now, at the end, out of these 6 predicted new modifications, 4 were realized. Well, this was a lucky instance because these phases just formed by increasing the pressure, and so it was easily realizable. Of course, the other phases the structures will exist as well, but this would require different methods of synthesis. So this is a proof of concept. So this is telling you that our approach of rational synthesis planning and solid-state chemistry is possible, and it is feasible, and it is physically correct, this picture, this approach, and also this view that we see so many structure candidates. Also, this is correct. Many colleagues, well, when I presented my talks showing maybe for a certain compound 10 different modifications, they were leaning back in their seat and smiling mildly, telling, yes, well, dream on, these are just pipe dreams. No, this is the reality of chemistry, and this is all waiting to be discovered, and it's enormous, and the hits are a certain number, and many other systems we have investigated where the predictions were afterwards confirmed by experiment. Well, now in parallel to these computational work and this systematic world on the concept, of course, we continued in working in the traditional way of solid-state chemistry, just this experimental exploration by trial and error, just doing these shake and bake reactions with different combinations of elements. And I'll just explain a few examples to you, which are very illustrative in the light of what I said, reported before. And again, I go to the roots of my academic career. In Germany, when a young scientist wants to start an academic career, he has to start a completely new field of research. So he was not allowed to continue the subject of the PhD thesis or on the field of his postdoc supervisor. A completely new field needs to be started. And one of the projects I started is explained by these cartoons. You all know that the equilibrium pressure of an oxide, according to Van 't Hoff's equation, grows exponentially with a linear increasing temperature. And I was imagining a compound that requires synthesis conditions that lie outside this stability regime. This is the regime of stability for this oxide, and the conditions lie outside. So it will never be possible to obtain this compound. So of course the measures are obviously you have to go from lower the temperature and move into this field of stability, or you have to increase the pressure, the external oxygen pressure, to overcome this decomposition pressure. And this is what I exactly did. And for this, I designed these autoclaves, which are suited to work in serious experiments. So we could really use it frequently and have high throughput experiments. And this has been a very prolific approach. and could make some new binary oxides and so on. But the most important achievement was that we could react oxides that are very labile, so they that would decompose before reacting in an all-solid-state reaction. One of these oxides is, of course, silver oxide that decomposes at 180 to 200 degrees centigrade, and normally you cannot perform solid-state reactions at this temperature. And using this approach, this methodology, it was like entering a new continent where thousands of new compounds could be made. And you see here, using this tool, one can react silver oxide always with any other binary oxide from the periodic table. And you see here some of these successful syntheses. Well, you may say, well, this is boring. Just replace silver by sodium, then it's sodium 2 SiO3. Well, it's an analog to all this alkali metal stuff. So this is not new. But in an inductive approach to gaining knowledge, of course, one is looking at the structures and one is comparing. And it became obvious already from the first examples we synthesized that these oxides containing silver are dramatically different compared to the alkali metal compounds. And what you see here, the gray balls are silver ions, all charged 1+. And they are simply ignoring Linus Pauling's rules. He will start rotating in his tube when seeing this. So they aggregate, although they are carrying the same charge. You see here parts where silver atoms only see other silver atoms, not an oxygen atom. So this is an amazing observation. And so more importantly, this proved to be valid for all compounds that contain a certain amount, a minimum amount of silver atoms. So with silver sulfate, you would not see it, but these compounds, you see it, and with every of these new and each of these new compounds, this was seen. And so they not only cluster, what is interesting, the distances, the silver-silver distance are the same as a metallic silver, and the topologies, the shape of this structure is also are sections of the structure of metallics. You see all these triangles belonging to the close-packed structure of silver. And as we know, structural peculiarities would also have as a consequence special properties. And this was observed already by the color. And you see here 3 examples. And we really showed that it's truly monovalent silver by EPR. So there are no spurious spins. These are closed shell materials, all of silver 1+. And you see, starting from silver sulfate, this conventional silver salt, the absorption edge is shifted by as much as 15,000 reciprocal centimeters up to the bathychrome direction. So there's a dramatic change in the bonding properties, and also the semiconductivity, the band gap is lowering with increasing the silver concentration. Well, after we had harvested a certain number or a large number of compounds, I decided to publish a review article, and this was done here with this title, Homoatomic D10-D10 Interactions, Their Effects on Structural and Chemical and Physical Properties. I called these interactions, there seemed to be some bonding interaction between these positively charged silver atoms, and the big surprise was, silver plus is a closed shell species. The D10 shell is closed. All shells are fully occupied. So it's absolutely hard to imagine how a bonding should be possible. And this homoatomic D10-D10 interaction or bonding interactions, I said in the beginning, they were picked up by others, by my friend Hubert Schmidbauer, for instance, who applied the same view to his gold compounds in coordination chemistry and metal organic chemistry of gold. And he coined the term aurophilic or metallophilic interactions, and some people call this what we discovered first, the argentophilic interactions. And in this essay, I made a prediction. I said, if there are structures that are so much similar to the structure of elemental silver, but the itinerant electrons are removed, only the silver plus cores are left, then these structures should be able to accommodate additional electrons. That would mean this compound should be able or capable of forming subvalent silver compounds. And the amazing thing is, we really found some of them, and the span of discovery of these compounds was several decades. So only some singular events at the beginning. And I start with, only show a few examples. I start with the first one discovered. It is this germanium silver germanate. And in the title line, this formula, this is not a typo. So this is the true composition, stoichiometric. And you see this shiny green material. And if you look at the structure, you first will notice that the germanium 04, it's an orthogermanate, and this tetrahedron is completely complies with the geometry known for such tetrahedra. This is telling us that this unit is electron precise. So this is a germanium 04 4-. And then we see some individual silver atoms not clustering, and others that are aggregated to form an octahedron. And the electron count is like this. These are the normal monovalent silver atoms, and these octahedra have kept 2 of the original electrons. Only 4 are dismissed and 2 are kept. And the understanding, I suggest a qualitative understanding, is just keeping in mind that it is an insulator, it is not a metal. It's a very low resistance, and it has a band gap, and it's diamagnetic. And of course, that is meaning that the electrons have to be localized. And one immediately sees the parallel to the borane clusters, octahedral borane clusters of B6H6 2-. And these are the skeleton molecular orbitals, the lowest lying one, and only the very lowest, the total symmetric one, seems to be occupied in this octahedron. So this is an octahedral cluster with the lowest count of electrons ever seen. But it's a meaningful picture of this. Now to more recent examples, very recent examples, and with really surprising, very much surprising structural features. This silver borate, you see it's very rich in silver. This silver borate, to describe the structure, it's easiest to start with the structure of metallic silver. So the balls here shown are representing a face-centered cubic structure. And if you replace 4 of these silver atoms adjacent, forming a tetrahedron by boron, then you get the framework of silver 16 boron 4. And then oxygen atoms are bridging over the edges of the tetrahedron, and each boron is bearing a terminal oxygen atom. And then you end up with this compound, and this B4O10 entity is isoelectronic with the phosphorus 4 entity. And you see the similarity to the metallic structure of silver is kept throughout. All cations form this cubic face-centered structure, and in the voids, these complex borate anions are inserted. And if you look at this anion, which was seen here for the first time in a fully integral shape and fully ordered, there were some proposals made with disordered such anions. You see immediately this is electron precise. And the electron count includes, in this case again, an excess of 8 electrons. There are 8 homeless electrons. And again, they do not give rise to metallic conductivity. They do not give rise to paramagnetism. And so we have to look again where these electrons are hosted, so they should be localized, and they should be localized pairwise. And this is a section through the structure. Of course, these voids are capped with blue octahedra of silver again. And this structure contains units of 4 attached octahedra. And in these voids, where no oxygen is looking into this void, there the silver-silver distances are contracted. This is interesting because there's no external force was making these shorter bonds. And here's one of these sites, and below this upper atom, there's another side of the same geometry. So if you count these contracted tetrahedra, then there are exactly the number of octahedra required for accommodating these 8 extra electrons, 4 extra electron pairs per unit cell. So this is very well settled, so there's no doubt that this view is correct. So we proved this, of course, by band structure and calculation and by analysis of the electron density distribution, and in particular by investigating the electron localization function, the ELF. And the ELF, maybe you're familiar with this, is a method to spot bonding electrons. And if you apply this, then the ELF always generates contours where in the heuristic conception of chemists, one would expand a bond. And indeed, what one sees here in this shrunk tetrahedron, there's an ELF contour, so there's electron density or localized electrons. So this picture is complete now. Now, another recent example, quite exciting again, and maybe for you in Delhi, maybe exciting to see that Govind Thakur prepared this compound. He's a very successful, extremely successful postdoc in my group. Now he has left. And he made this compound. And again, an amazing structure. If you look at platinum and silver, they jointly form a cubic close-packed arrangement. And this is perpendicular to the layers. And of course, there are slight deviations because there's oxygen included somewhere, but it's amazingly well fulfilled all the conditions of this packing. And to see here are layers consisting only of silver, and above and below there are broken layers. And if you look at these layers, then this slab results. And the middle layer in the paper plane is a hexagonal packed layer. All atoms are present. And then there are triangles on top and triangles below. And this way, cube octahedra are formed. And these cube octahedra are connected via common edges to form this 2-dimensional slab and arrangement. And here, again, the suspect short distances are found. So we will just inspect the electron count. For this purpose, we have to look at the platinum-oxygen partial structure. And this is the platinum-oxygen partial structure, again, a 2-dimensional slab, and it's easy to understand. So there are 3 octahedra edge sharing on top and the same unit on the bottom against edge sharing. So a puckered slab forms. And this is the first time that one sees a 2-dimensional slab of this type. And again, the bonds are exactly the bonds you would expect for platinum 4+. And so this is telling us that the electron count goes like this. And this is meaning that for this composition, 9 electrons are in excess. And so that means 1 electron per formula unit. And again, this compound is diamagnetic, insulating, or semiconducting. And so the electrons have to localize pairwise. And this is what was really found. And it is exactly, again, in these tetrahedral voids within the cube octahedra. And here you see, again, this absolutely amazing structure. So there's such a layer almost of metallic silver, then the oxide platinum layer, with these 3 octahedra on top and 3 octahedra on the bottom. So amazing structures were encountered, and I just showed you one former one just because for its beauty. And the composition is silver 13, osmium 06, a tremendous amount of silver. And now these are icosahedra of silver and centered by silver atom. So these are arranged in the cubic primitive fashion, and the osmium 06 octahedra are inserted in this voids. And the electron count tells us that, and theoretical analysis, that this is osmium 8 plus. Hard to believe. Osmium 8 plus in a neighborhood to almost metallic pieces of this elemental silver. And I should add that the distances between these clusters are also quite short, so that one really could say this is an arrangement of a 3-dimensional metal where somebody drilled some holes into it from all 3 directions. And you see from the orientation of the octahedra and the surrounding, this window is rotated against the square of the octahedron. This is telling us that overlap between these 2 partial structures is only possible via s electrons, otherwise no overlap, no communication between these 2 faces. Well, now just this overview. As I said, over the years, we discovered all these compounds, and now we believe many more of them should exist, and we do not understand why and where they form. If you look at this counter cations, this seems to may happen everywhere. And now we come to the question of rational material synthesis, our concept of predicting compounds capable of existence by global exploration of the potential energy surface. And I think what would never have been able to discover these compounds along these tools, because already in the beginning, the binding between the closed shell silver plus atoms is not understood, or it is impossible to include it into a quantum mechanical code. It is only a kind of dispersive attraction, but it's not like with the noble metals, so it must be somehow different. And this proximity of these silver atoms in these silver-rich oxides is the precondition that additional electrons can enter to make these subvalent compounds. And so you see, with just these computational techniques, one would never have discovered these materials, these oxides. Well, I'll show another example, and this is from the field of these alkali metal cesium. So this is a very small class of compounds. You may even say it's a bit exotic. It's nevertheless a very important family, because it is representing one of the very rare cases of mixed valency and open shell nature in the oxide sublattices. And only the rubidium and cesium representative were known. And so this is the high temperature form, and there is charge disordered. So these dumbbells are disordered, and it has been shown by vibrational spectroscopy that these are truly superoxide and peroxide. So there's no intermediate and no metallic character. Also, this has just this localized electrons, however disordered. And so here we see why it is so important, interesting. You know, for transition elements chemistry, the open shell transition element chemistry, all these degrees of freedom for order and disorder are extremely important also for the functionalities. And mainly these features are studied in open shell d electron systems and f electron systems. And interestingly, this system shows the same kind of disorder as in these transition metals. So there's charge localization and delocalization. That means an insulator metal transition. Could be seen, but we did not observe so far. Then we can observe charge ordering and related to this structural relaxation, orbital ordering, spin ordering. And this all has been discovered. And even that this is a kind of Verwey type, shows it Verwey type of transition. That is a very prominent transition type, first time observed with magnetite, with iron oxide. Well, now, of course, all these effects should be stronger when the alkali metal ion is smaller than the one used so far, rubidium and cesium. And I told my technician, Patrick, try and synthesize potassium 406. And this was the reaction envisaged. And he tried many times. And he said, no, it doesn't work. And I told him, you know, all things rubidium can do, this can also be done by potassium. So I'm absolutely sure this compound will exist. Try harder. He got a little bit angry or whatever, upset, and he said, I want to see that. And he prepared this experiment. And here the pellet or the starting materials in the glass tube under argon and heated it gently with a Bunsen burner. And you see the color starts changing to black while you're observing it. So it's a very fast reaction. And the black color is a first indication that really the sesquil oxide has formed, because the sesquil have this black color. And after a moment of great joy and pleasure, seeing that the reaction really had worked, the disappointing moment came, things went back. So it decayed again. And you see, this is a compound that is only capable of existence at high temperatures. And you see, moreover, the process is reversible, fully reversible. And here are the photographs of the intermediate stages. And this reversibility shows you that all things were running in equilibrium, and is giving a special information that such a compound is only stable at high temperatures. And the explanation is, of course, that according to the Gibbs-Helmholtz equation, which applies here because we are really working in equilibrium, that the entropy of reaction has to be positive, and the gain in entropy is enhanced by this concept of this term by growing temperature. At high temperatures, the gain in temperature overcomes the loss in entropy, and the compound starts to be stable. And if you look at this equation, all solid materials, you do not see any source for gain of entropy. And the gain of entropy is exclusively electronic in nature. In these compounds, in potassium peroxide and in superoxide, all electrons are strictly localized and they don't have any choice. In the sesquil oxides, there are 3 dumbbells that share 1 electron. So the electron has a chance to enter one of these 3 oxygen dumbbells, and just a rough estimate of the entropy gain by this ends up with these numbers. And at the reaction temperature, this would be about 82 kilojoule per mole. And by comparing the electrostatic part of the lattice energy for the start materials and the product materials, tells that this is positive. So it is from the electrostatic part of lattice energy, it is better to stay apart. And so this is exclusively stabilized by entropy and by localized electrons. This is an extremely interesting feature. And this has been confirmed by qualitative estimate by precise calculation by Freisold and Neugebauer, who are experts in calculating entropies of solid materials. So it's an amazing finding, and I had really bad dreams at night already, imagining how many compounds we overlook that are stable at higher temperatures, and we did not see because the crucibles we are using are intransparent. So it is an amazing effect. Now, again, back to my issue of synthesis, of rational synthesis planning. And it is obvious that it would be impossible to find such a compound. Of course, you will never find compounds on the potential energy surface that are entropically stabilized alone. So there are other cases known. Again, normally you would not find any glass structure on this surface. But you can use the crystalline silica maybe and generate by disorder the glass structures. But this is a one step much more complicated. So one has to predict how these electrons would behave. So do they really localize as particles? And only if they localize as particles in a disordered scheme, then they contribute to entropy. And this is another thing that would be impossible to predict. So now you see why I use this title for my talk. So just not proof of concept, but failures of concept. And this is telling us we have to continue to work in this explorative fashion, in this inductive way of gaining knowledge in solid-state chemistry. And I'm absolutely convinced all these new methods of data mining, of machine learning, and these global searches we did, and others joined us in the business. This will never, I think, really say never, will be suited to discover everything. So their nature is so inventive to find new things that are not included in these calculations. And so my message at the end is, so there's plenty of room for explorative solid-state chemistry. And of course, what do you need for success in this direction? You need inspiration, creativity, and solid and perfect craftsmanship. So the methods, the style of working must be really perfect. Then one will enter into more and more new systems. And of course, one also needs some good luck. And this is said by the sentence, serendipity favors the prepared mind. Good luck. And you must see what happens. So many people overlook the most exciting results. And interestingly, this idea was expressed already in 1855 by Louis Pasteur, the famous French scientist. La chance ne sourit qu'aux esprits bien préparés. Well, I thank you so much for your attention and for your patience, and all collaborators. Of course, over these decades, I've represented work. These have been many, 20 or more, and I just do not mention and do not bring the list. And I gave all the citations on the slides. Again, thanks to the collaborators. And I was really in the lucky situation to always have very motivated and skilled collaborators. Thank you very much.
Yeah. Thank you, Professor Jansen, for the insightful and stimulating talk. So the floor is now open to questions. I request all the attendees to please type their questions in the chat box, and we can take it to the speaker. So our webinar is also being telecasted or webcasted through YouTube, so we might have some questions from there too. Okay, so the first question is actually from the audience. I just put it here. So Professor Jansen, will you be able to take some questions now?
Yes, of course. Yeah.
Okay, thank you. Yeah. So the first question from the audience is, in case of Fe3O4 nanoparticles of 8 to 10 nanometers, we often see that there are some magnetite layers on the surface. Now, if the nanoparticles have a magnetite phase at the core with a very good stoichiometry and a thin shell of magnetite 2-3 nanometers, can it show Verwey transition?
So I'm not aware of this finding, but the problem, of course, I would not say a problem, but of course we always have to keep in mind that there is a difference between this ideal view on these infinite crystals and the nanoparticles. And because by generating smaller and smaller particles, then surface effects, we all know this, are becoming more and more important. And so it can well be, but we never worked in this field, in this region of size controlled, grain size controlled chemistry and physics.
Okay, okay.
So maybe did I get the question correctly? So there was a question on magnetite nanoparticles, and the surface was behaving different from the bulk, or?
Yes, yes. I think
so. Unfortunately, I cannot answer this because this is not so much my field. But of course, we know even if you look at the work by Alexandra Nawrotsky, who did thermodynamics, and she showed that if you go to nanoparticles, even other modifications are becoming the ground state structures. So there's of course a lot of changes in this case.
Okay, okay. So any other questions from the audience? Okay, so while we wait for some of the questions, so I have a kind of question like, since we have a lot of our young students attending this webinar, they're at the master's level or have just started on their journey for the PhD program. So what suggestion would you like to give these budding young researchers as they take their baby steps into research?
Well, this is a very difficult question, and it is just a case. It's always an individual decision. You know, from my side, so I always did things I like myself. So it has to please my own demands and expectations. I was not looking at what other people say to it and whether they like it or not. But I do not know if this is a clever idea nowadays. So science has become more and more a social event and to have to be accepted by others. And so my answer is twofold. So if you want to make a career in a political sense, rather, then one should go mainstream. Yeah? And if you want to please yourself and get really new insights, well, then you go the risk that you are just an individual person and maybe this will not be so much accepted. So it's difficult. And now my conclusion would be to follow the own ideas and the own gifts, so the own strengths. Everybody should be able to judge where are the strengths. Am I a very good experimentalist, and I'm a creative chemist, and so on, or I'm rather a theoretician and I'm very good in theoretical physics and theoretical chemistry. So my advice would be always to follow the own capabilities and their own wishes.
Okay, okay. I think that would be really useful for our young audience. So we have another question from Professor Ngole. So in case of AG7 PT207, is it possible to tune the band gap as a function of AgPT composition?
No, these are all stoichiometric compounds. And even if we play with the silver to platinum ratio, then only this phase forms and platinum or silver is left over. So this is an amazing thing that these subvalent compounds are really Daltonite compounds, as one says. They are stoichiometric and they have almost no homogeneity range. But to go a little bit further than your question, so we see that one of the oxygen atoms can be, from a threefold crystallographic position, can be easily removed at 150 degrees centigrade. One of the oxygen atoms is leaving the structure. And this would be a kind of doping, as you suggest.
Okay. Okay, so any other questions, please feel free to type in the chat box. Okay. Okay, so there is a continuation. So further, what about tuning the band gap by changing the size? So that's the continuation of the previous question.
Yeah, okay. It is again a question from nanochemistry. Yeah. So of course you can. It is known that for any compound you may tune the band gap by the size, and even do see a transition from bands to molecular orbitals. If you make the cluster smaller and smaller, then you end up with. And in our case, if this question is referring to our compounds, subvalent compounds, it looks as if we really see these molecular orbitals in these silver clusters. So, and I did not say explicitly, but all these stabilizations of clusters with these 2 electrons in the lowest orbital, molecular orbital, are reflecting a kind of borane chemistry, just kind of weight clusters, just transformed to silver. And it's the first time that these ideas can be transferred to a heavy atom and to a transition metal.
Okay.
Martin,
So, yeah.
I had just a comment. So what about your, did you look at gold, substoichiometric gold compounds? Because did you look at?
We also did a lot of work on gold, and mainly it was focused on gold 1 minus, the negative gold and the relativistic stabilization. It's an extremely interesting field, and you are addressing just the point where we start. So I started with my autoclave, so you know I retired long ago, with a young guy at Cologne. And one of the ideas is to try to make gold 1 compounds, oxides. And amazingly, like silver, we have silver 6, silicon 207. Yes, just a disilicate. And such a compound with gold does not exist. And even a telephosphatide with gold, it should be possible to make gold 1 indium O2, you know, these layered telephosphatide. And none of them is existing, but we are tackling this problem. It's a very good question, very good idea. I think it will be extremely interesting because gold has these relativistic effects, and in these compounds, gold atoms would approach each other very much. So there should be interesting physical effects. Yes, indeed.
Okay. Okay. So any more questions from the audience? Yeah.
No, I think Martin gave an excellent talk. I just want to thank him again. So on behalf of chemistry, maybe Somik, you can thank Martin.
Thank you so much. And again, thank you for inviting me. It was a great pleasure. And I hope that I will be able to come to India soon.
Normally, we see you in winter school in Bangalore, right? But
yes, maybe. Yeah.
This past 1 year, we have not met. So maybe next year.
That's not. Yeah. Okay. Thank you very much.
Yes. Yeah. Bye. So thank you. Thank you, Professor Jansen, again, and hope to host you in our institute physically someday when
so
all
now
this
you should come
gets over.
To Delhi. Martin should come to Delhi next
like
visit to Delhi.
Yeah. Okay. Thank you.
Yeah, thank you. And we would also like to thank the head of the department, Professor Anil Elias and Professor Ram Ramaswamy for their encouragement and support. And also please visit our Facebook page for more information on upcoming talks. And we hope to see you all again soon. Have a great evening. And thank you again, Professor Jansen. Thank you.
Okay. Thank you so much. And bye-bye. Bye.
Bye-bye.
Bye-bye.
Okay, Somik. Thanks.
Yeah. Sorry for the technical glitch today.
Yeah, okay. I think it's always the same when people don't switch off their mobile.